Hello, good evening, everyone. Am I audible? Hello. So, good evening, everyone. I welcome you to the week 3 live session for course non-conventional energy resources. The course instructor is Professor Pratap Haridos sir from IIT Madras, and I am his TA Amit Kumar Sharma. So today we will discuss about the week 3 content. So basically, every week we are taking the classes. So my class is on every Monday, 6 to 8 p.m. So in last two classes, we have discussed about the week 1 and week 2. Today we are discussing about week 3. Am I audible? Anyone? Yeah, is my laser pointer visible to anyone? Anyone can respond? Okay. Okay. So let's start with the week 3. So first of all, in week 3, we have discussed about the GDP and its connection with the energy use. So this is a graph. This is data from the World Bank from last many years. So it's data from 1980 to 2015. So there are two lines. You can say red one and green one. So basically, they are showing the relationship of GDP and energy use. Okay. So so as we can see that uh, as I think my pointer is visible to you. So as the red line is increasing, the blue line is also increasing. Okay. So basically, the red line is for energy use and the blue line is for GDP. So as we can see that as the energy use is increasing, the GDP is also increasing. So it's directly the GDP and energy is having direct connection. So basically, when we are using the energy, it means we are having more resources, we are having more technologies, and we are using more energy. It means the capacity of the people for that particular area, so they can afford more energy to use. So it means that they are having more money also, and the particular state or particular country is also like doing importing exporting as per the energy use. So the energy is directly connected with the GDP. So if the energy use is high, it means that GDP is also high for that particular area. So these are data for India. In left side, here you can see that. So here you can see that these five highest GDPs in India is first is Maharashtra, second Uttar Pradesh, then Tamil Nadu, Karnataka, and Gujarat. So these are the five highest GDPs in India. These states are having highest GDPs, GSDP. It's states GDP. Okay, so it's calling GSDPs. So these are five highest states having most GDP. So you can see that Maharashtra is having the power installed allotted capacity. You can see. So the Maharashtra is first in Western region. Okay, the power installed or allocated is highest in the first in the Western region. For UP, second in the northern region, Tamil Nadu, first in the southern region, Karnataka, second in southern region, and Gujarat, second in the western region. So here we can directly see that as the power is more, GDP is also more. Some state with lower power installed are Arunachal Pradesh, Manipur, Nagaland, and Mizoram. So in these states, the power installed allocated is not much as the above states. So the GDP is also not so high. So we can directly say that GDP is directly connected with the energy uses. So from this data, we can solve one simple question. As GDP of a nation increases, energy consumption generally. So if the GDP of a nation is increases, then what about the energy consumption? It's the options are increase, options are increase, decrease, remains affected, initially increase, then slightly, then steadily decrease. So as we discussed in the previous slide, that if the energy consumption is increasing, the GDP is also increase. So the correct answer will be increase. So the accepted answer is increase. Now the second question is, there is a one statement is given. Okay, so the statement is Maharashtra consumes more energy than Tamil Nadu. So basically the statement saying that Maharashtra is using more energy than Tamil Nadu. Then based on this above statement, uh, there is a conclusion. The conclusion is saying that based on trends usually seen in relationship between energy uses and economic activity in India. So basically the statement is Maharashtra consumes more energy than Tamil Nadu. Conclusion is based on trends usually seen in relationship between energy use and economic activity in India. So A is Maharashtra has more GSDP than Tamil Nadu, and B is Tamil Nadu has more industrial output than Maharashtra. Okay, so we have to say which conclusion are correct. Okay, so the first one is Maharashtra has more GSDP than Tamil Nadu. So from statement we can see that Maharashtra consumes more energy than Tamil Nadu means the A is correct. Maharashtra has more GSDP than Tamil Nadu. So conclusion A follows, and the conclusion A follows, but not conclusion B, because Tamil Nadu has more industrial output than Maharashtra. We will not follow, because if the industrial output is more, it means the GDP will be high. So as we know that A is correct, Maharashtra has more GSDP, then it means that industrial output is high for the Maharashtra, not from Tamil Nadu. Okay, and also these statements are not giving any information other than the GSDPs. Okay, so there is no other information mentioned on industrial output, so we cannot conclude about statement B. So based on the GDP and energy use point of view, we can say that only A follows, not the statement B. Okay, we'll come to the next. So this slide is showing the atmospheric CO2 concentration in ppm derived from in situ air measurements at Mauna Loa Observatory, Hawaii. So this is an observatory in Hawaii. So this observatory is recording the concentration of atmospheric CO2 for last many years. You can see that we are having data from 1960s to 2020. Okay, and the main thing is that you can see that as the year is increasing, the ppm level is increasing. Okay, you can see the increment, and you can see that from last you can see the from last 40 years, 40 or 30 years, the slope of increment is more steeper. It's going steeper and steeper. Okay, so we can conclude that you can see the slope for this area, and as compared to this area is more. Okay, so from last 30-40 years, due to the industrial revolution, due to the more use of energy, the atmospheric CO2 concentration is increasing very high. Okay, so you can see it's around more than 400. So it's around 425, as I remember. The current CO2 concentration is 425, which is very high. And we have some previous data also. like using bubbles of air trapped in ice, it has been determined that CO2 in air has never been above 300 ppm in last 4 lakh years. So you can see that from last 4 lakh years, the CO2 concentration have never above 300 ppm. But from, you can see from 1960 to 2020, from 1960 to 2020, it's just 60 years, and the CO2 concentration is from 300, like approx 300 to 425. So it's very huge increment. From last 4 lakh years, the concentration was not above 300, but only in this little time span. Because you know that this 60 years, the 50, 60 years, as compared to this 4 lakh years, is very, very, very small. Okay. So this is not a, even you can say you can compare it, because it's 50 years, it's very small time span as compared to 4 lakh years. So you can see the increment of CO2. So this is very dangerous for our environment. Okay. And due to the current energy use, if we are not moving away from the fossil fuels, if you are not moving toward the renewable energy, this CO2 concentration will become more high, and this is a huge danger to the environment. And as we currently see, we are seeing the global warming issues, we are seeing the climate change issues. So these are all the reason of this increased concentration of CO2 in the atmosphere. Okay. So the energy use in present form is changing environment in a never seen before manner. Okay. So from last 4 lakh years, the CO2 concentration was only 300, not more than 300 ppm, but only from last 50, 60 years, the concentration is more than, it's about 425. So it's very huge. Uh, all over the world, various steps are, the UN is also considering various steps, and every country is considering various steps to reduce the CO2 concentration, and like to move away from the fossil fuels to renewable energy. So maybe these steps will fruitful in the near future, and we will see the result. Is my pointer is visible to you? Anyone? Am I audible or not?
Yes, sir, you're audible.
Okay. Are you able to see the pointer or the marker I am using?
Yes, sir. It's visible.
Okay. Okay. Thank you. So this week content is about solar radiation. Okay. So what is the solar radiation, and what are the different aspect of this? So we will revise it. So first of all, solar radiation is radiant or electromagnetic energy from sun, and it provides light and heat for the earth and energy for the photosynthesis. So it's a very basic, because the heat for earth is very important. If there is no heat on the earth, the temperature will go in negatives. Okay. So there will only the cold environment, and the life cannot sustain on the earth atmosphere. Okay. And for photosynthesis, because we are getting the all our basic needs from the plants only, everyone is dependent on the plants. Okay. We are getting the oxygen, we are getting the food, and we are getting everything. The other animals are also getting everything from the plants. So they are producing this that products from photosynthesis, and for this they require some energy. So the solar radiation is giving the energy for the photosynthesis. So solar radiation is very important part to maintain the sustainable life, to maintain the life on the earth. So this radiant energy is necessary for the metabolism of the environment, its inhabitants. It's very important. If the radiant energy is not in the balanced form, then it will be very difficult, or you can say the environment, the metabolism of the environment and inhabitants will be not possible. So basically there are the three relevant bands or ranges along the solar radiation spectrum are ultraviolet, visible and infrared. So the solar radiation are coming, and there are basically three band gaps in which the radiation are coming, that are ultraviolet, visible and infrared. We will see in next slide that what are the what are the wavelength ranges for these three. So just remember now, ultraviolet, visible and infrared. So these radiation spectrum are coming in the solar radiation. So of the light that reaches Earth's surface, infrared radiation makes up 49% of visible 49% of, while visible light provides 42.3%. So you can say the major portion of the surface is from infrared radiation. It's around 49.4%, and visible light is around 42.3%, and remaining around 8% is ultraviolet radiation. So UV is very less, major is infrared radiation, and second is visible light. Each of these bands has different impact on the environment. We will also discuss what are the impact of these radiation or these bands on the our environment. We will also discuss in our upcoming slides. Now, the amount of intensity of solar radiation that a location or body of water receives depend on variety of factors. So we know that solar radiation will depend on variety of factors because we know the Earth is rotating, okay, in a particular orbit, and it's revolving around the sun. So there are various factors. So these factors include latitude, season, time of the day, cloud cover, and altitude. So these are some important factors on which the amount of intensity of solar radiation for a particular area or particular location will depend. What is latitude? What is the season? Time of the day? It's daytime or nighttime? Cloud cover. So like what is that? How much cloud is there in the sky, or about the atmosphere and altitude also. Not all radiation emitted from the sun reaches Earth's surface. Much of it absorbed, reflected, and scattered in the atmosphere. So the Earth is radiating more energy, but the all energy is not coming it to the Earth's surface because there are various layer of atmosphere also. So most of it absorbed, reflected, and scattered. We will see in our upcoming slides. At the surface, solar energy can be absorbed directly from the sun, called direct radiation. So the energy that is directly absorbed directly from the sun on the surface, it's called direct radiation, or from light that has been scattered as it enters the atmosphere, called indirect radiation. And some is scattered and then coming, that is called indirect radiation. So these are the like two diagrams. So you know that we know that that any wave is in the the energy is coming in the waveforms. Okay, so we are measuring the wavelength, the distance between two peaks of the wave. These are the two peaks of a particular wave. So the distance between these two peaks will measure the wavelength. Okay, so the wavelength cycles are measured in nanometers. So normally the cycles are measured in nanometers range. Okay, from the peak to peak, the shorter the wavelength, the more energy it has. Okay, so the shorter the wavelength, so the shorter the wavelength will have more energy. Okay, so you can see in this diagram there are three wavelengths as shown: blue, green, and red. So you can see that the distance for the blue line as compared to green as compared to blue. Okay, so the lowest is for blue, second one is green, and the last one is red. So the lowest one will have more energy. Okay, so the blue light has more energy than red light, because the wavelength for the blue, you can measure distance, this distance 1, distance 2, and distance 3. Okay, so you can measure distance from peak to peak for blue, peak to peak for green, and peak to peak for red. So we can see that for this blue, the distance is less as compared to the red, and green is in between. So the blue one will have more energy as compared to the red one. So when we see the spectrum of the sunlight, then basically there are three spectrum we have discussed in the last slide: that ultraviolet UV, visible light, and infrared. So UV is having more energy. So the UV is blue. UV is represented by the blue color. Then infrared is having more energy, and then visible light. So infrared will be generated from the red one, and the visible light is from green color. Okay. So the ultraviolet light, which has the highest energy, can cause damage to DNA and other important cellular structure. So these UV rays are very dangerous to our health, our bodies, for animals and everyone. So our atmosphere are having various protective layer. So they are like they are they are like, you can say that not able to, not allowing the ultraviolet light to reach the surface, but the ozone layer is protecting our earth. But due to the global warming, ozone layer is also depleting, and ultraviolet lights may come to the earth, and that is very dangerous because they are having more energy, so they can damage the DNA and other important cellular structures because they are having more energy as compared to the infrared and visible light spectrum. So in this diagram, you can see the electromagnetic spectrum. Okay, so this is the range for UV, this for visible light, and for the infrared. So the infrared light is red, the UV light is represented from blue, and visible spectrum is green. Okay, so the wavelength range for UV light is around, wavelength for UV light is from 100 nanometer to around 400, and for visible it's 400 to 700, and for infrared it's about 700 to 1 mm, 700 nanometer to 1 mm. So this infrared radiation is having huge wavelength spectrum as compared to the UV, and visible UV is having very less. And we have also discussed that infrared light is making around 49% of energy contribution on Earth. Visible is 40 around 2%, and UV is only 8%. Okay. So sunlight or solar radiation spectrum includes band between 100 nanometer to 1 mm, which encompass ultraviolet, visible, and infrared radiations. So you can see that ultraviolet is coming from 100 to 400, then 400 to 700 is visible light, and from 700 to 1 is the infrared. So now in this slide, we will see some sample calculation to how to calculate the energy that we are receiving per day, or you can say the how much energy we are receiving from the sun. So this diagram is representing, this is the sun, the yellow one. So the sun radius is 0.7 million kilometer. So it's having a orbit, and the radius of its orbit is 149 million kilometer. In this orbit, from the dotted line, you can see in this orbit the earth is rotating. Okay, so the earth is moving in this orbit around the sun. The sun is here. So the earth radius is around 6371 kilometer. So the earth radius is very small as compared to this orbit radius, and as compared to the radius of the sun. So sun radius is having 0.7 million kilometer, earth radius 637 kilometer, and earth is rotating in this radius of the orbit around 149 million kilometer. So the surface of the sun is around 5500 degrees centigrade, and the core of the sun is around several million degrees centigrade. So the core temperature is very, very high in million degrees centigrade. The surface is around 5500 degrees centigrade. So from the basic calculation, the sun gives out around 384 iota watts based on the this temperature. You can find out the temperature, the energy released from the sun. So it will come around 384 iota watts. Iota we have covered already in our previous classes. The 10 is to power 24 called iota. Okay. So you can say 384 into 10 to the power 4 volt and 3.84 into 10 to the power 26 volt. So this energy is sun is radiating. So if the surface of the sun is at temperature of 5500 degrees centigrade, so sun will radiate around 384 iota watts. Okay. Okay. Now we have to find out the intensity of sun's radiation at Earth's orbit. So we know the radius of the Earth orbit. It is around 149 million kilometer. So it's in a spherical form, and we know the area of sphere is 4 pi r square. Okay. So we know total energy. We know the radius of the orbit. So we can find out how much energy is coming at per meter square. So just divide this total 3.8.26 watt by the area. This 4 pi and this is radius r square. Okay. So r is, you can see that 149 million kilometer can be written as 1.49 into 10 to the power 11 ka square. So this calculation will give you 1377 watt per meter square. So 1377 watt per meter square of energy is coming from the sun to this orbit. Okay. So the at orbit, which is around 149 million kilometer radius. Okay. So the energy coming from sun is around 1377 watt per meter square. Now let's consider how much energy is coming to the particular on the earth only. So as we know, the earth in spherical form. So you can see this in a spherical form, but at a time only this section, suppose here the sun is, so only this section is facing the sun, so this section will only receive the heat. So we can consider it a circular disk. Okay. So we will find out the area of the circular disk. So we know the radius 6371 kilometers. So the area of circle is pi r square. Pi r square. So the area will come out around 1.27 10 to the power 14 meter square. So the area of Earth which is receiving the radiant energy from the sun is 1.27 into 10 to the power 14 meter square. Now we are having the total energy. The intensity of sun's radiation at Earth orbit is 1377 watt per meter square. Now we know the area on which this energy will impact. That area is Earth's area, and that is 1.27 into 10 to the power 14 meter square. Now multiply with this area 1.27 into 10 to the power 14 into 1377. This will give you around 1.75 into 10 to the power 17 watt or joule per second. So this much amount of energy. So 1.755 into 10 to the power 17 watt of energy is coming to the earth from the sun. Okay. So energy received from the sun by the earth each year. So this energy is coming or joule per second Okay. So we convert this into year. So multiply by 60 for minutes, multiply by 60 for hours, multiply by 24 for days, and 365 for 1 year. Okay. So this 60 is converting seconds to minute, this 60 converting minutes to hours, this 24 converting days, and this is for year. So when you multiply all these data, it will come around 5.5 into 10 to the power 24 joule. So the energy received from the sun by the earth each year is 5.5 into 10 to the power 24 joule. Okay. So you can say 5.5 million exajoules, because we know 10 to the power 24 is called as exa. These units have covered in the week 1 lecture. If you are like having difficulty in reminding these, so you can revise the week 1 class. In that class we have discussed about various type of units. Okay. So 10 to the power 24 is iota, 10 raised to power. Okay, this is exa, 5.5 million exajoules per year. Okay. So humankind use around 500 exajoules energy per year. So this is the energy used per year from the humankind, and we are receiving 5.5 million exajoules per year. So in the previous slide, we have calculated how much energy the Earth is receiving from the sun per year. So this is 5.5 exajoules, and humankind, how much energy a humankind all over the world is using per year is around 500 exajoules. So you can find out that in how much time this 500 exajoule energy the Earth will receive. So just divide it 500 upon 5.5 into 10 to the power 6 equals to 9 into 10 to the power minus 5 years. Okay. So divide this 500 by this. Okay. So 10 to the power 18 is exa and 10 to the power 24 is iota. So this 5.5 million exa, it means we have to multiply it with 10 to the power 6. So that's why 5.5 into 10 to the power 6, because it is 5.5 million exa. Okay. Because it was in 20 10 to the power 24. So we have converted it to million and multiplied with the 10 to the power 6. So 5.5 into 10 to the power 6, it's coming around 0.033 days or 0.79 hours. So you can see it's we are receiving the per year energy we are using. The all humankind in the earth at the earth using 500 exajoule per energy, and we are receiving this energy from sun in just 0.79 hours. And suppose you are considering the efficiency of 30%. Okay, since 30% of the incident energy is reflected back on the surface of the earth, the energy used by the humankind each year is received in, because suppose 70% energy is only just coming and 30% is reflecting back. So divide this in by 0.70, so it's around 1 hour. So roughly we can say that the energy we are using in 1 year, okay, that's very important fact. The energy we are using in 1 year, we are just receiving that energy in 1 hour from the sun. So we are having ample scope of to tap off this energy. Okay. So currently we are using that the current use of energy is coming from fossil fuels, and the fossil fuels is the main reason that is increasing the CO2 concentration in our atmosphere. And even in our previous slides we have seen that the CO2 concentration is around more than 400 ppm, and it was in last 4 lakh years it was not more than 300 ppm, but in last 50-60 years it has crossed 400 mark. Okay. And if we are not change our energy use, our the resources from which we are tapping off the energy, this data will go more. Okay. So from this data, from this calculation, from the previous slide and this slide calculation, we can see that our all requirement, our whole year requirement, the sun is fulfilling in just 1 hour. Suppose you are having some technology that is only able to tap off a very fraction amount of energy, then only you will get the complete requirement 1 day or 2 day. Okay, because the complete energy is coming in just 1 hour. So there's ample scope to tap off the sun's energy. Okay, to fulfill our daily energy demands. So that's why currently we all over the world we can see that every nation is working toward solar photovoltaics, because that is the best way to use the solar energy. Okay, because it can convert the energy directly to the electricity. There is no combustion, there is nothing, just the solar radiation are directly converting to the electricity. So all over the world every nation is focusing on solar PV now. So in conclusion, we can say that earth receives nearly 5.5 million exajoules of energy from sun each year. The earth receives nearly 5.5 million exajoules of energy per year from the sun. Okay, and we are just using 500 exajoules per year. So in 1 hour we can receive the complete energy that we will use for 1 year. The entire energy used by the humankind each year is received on the surface of the earth from the sun each hour. So it's very important aspect that each hour we are receiving the entire energy of humankind that is used by the whole year. Okay, now come to next slide. So this is very important slide. In this you can see that earth's energy budget, that how much energy is coming and where that energy is going. Okay, so this is the sun and this is surface of the earth. This is the sun. So you can see various arrows. So these are the basically energy balance. So suppose 100% energy is coming from sun. So 100% is around 174 picowatt. So 174 picowatt is energy coming from the sun. So that is coming. So from this 174, 6% is reflected by the atmosphere. Okay. So from 100%, 6% is reflected back. So remaining 90% is going towards the earth. Okay. Again, from this 96%, around 16% will be absorbed by the atmosphere. Okay. 6% was reflected, 16% was absorbed. Okay. Then remaining light again coming towards the earth. Then 20% is reflected back by the clouds. Okay, so 20% will be reflected back by the clouds. Then further coming, then 3% will again absorbed by the clouds. So the remaining energy again coming. So again, the 4% will be reflected from the earth's surface. So when this remaining energy is striking the earth, so 4% will be reflected. So remaining only 51% energy is absorbed by the land and the ocean. Okay? So when 100% energy is coming, but only 51% is absorbed by the land and ocean. So remaining energy, remaining 49% energy is either reflected, either absorbed by the clouds or atmosphere. Because you can see the 6% is reflected from atmosphere, 20% was reflected by the clouds, 4% reflected from the earth's surface, 1.6% was absorbed by the atmosphere, 3% was absorbed by the clouds. Okay. So this remaining energy is coming to the earth surface, that is 51%. So the 51% energy is absorbed by the land and ocean. Now again, now the 7% of this energy is used in conduction and rising air. Okay. So due to some temperature difference, the conduction is happening and the temperature of air is changing. So the 7% energy will use in conduction and rising air uh, carried around 23% energy carried to the clouds and atmosphere by latent heat in water vapor. So 23% energy will be carried to the cloud formation. Okay, so that energy is coming used by the cloud formation. Okay, and atmosphere by latent heat in water vapor, and this, and you can say the is the amount of this energy around 15% will be again this earth surface is also radiate. Okay, so 15% will be radiated to the atmosphere. Okay, and then further you can say further directly go to the space, around 6% will go to the space. So the 64% radiated to the space from clouds and atmosphere. So the clouds are formed, so that 64% is used in radiation to the space from clouds and atmosphere, and 6% radiated directly to space from the earth. Okay, because in night time uh, the sun is not facing the earth for particular area, so at that time the temperature of the earth is more than the space. Okay, so the space will radiate the energy to the earth will radiate energy to the space. Okay, So this is the complete Earth's energy budget. So how much energy is coming from the sun and how much it is bifurcating in various aspects. Okay. Now next slide. Now we see the how the greenhouse effect is happening. It's very important greenhouse effect because current issues of climate change, global warming is only due to this greenhouse effect. Okay. So again, this is a simple diagram. This is explaining. So Earth's surface is it's also atmospheric, but thin layer. You can see na. This thin layer is represented by the atmosphere, and this is the Earth's surface. So the solar radiation is coming from the sun. So most radiation is absorbed by the Earth's surface and warms it. Okay. So the most of radiation is absorbed by the Earth's surface and warms it. Some solar radiation is reflected by the Earth and atmosphere. You can see that these are reflected from the atmosphere, and this from reflected from the Earth's surface. Now, uh, okay, so some of the infrared radiation passes through the atmosphere. Some is absorbed and re-emitted in all directions by greenhouse gas molecules. The effect of this is to warm the Earth's surface and lower atmosphere. And infrared radiation is emitted by the Earth surface. Okay, in our previous slide, we have talked about the wavelength. So the shorter the wavelength, the more the energy is having. The longer the wavelength, less energy is having. So the most of the light, okay. So the infrared portion. So because you can see the Earth's surface is again radiating. So this radiation will be in infrared portion. Okay. So some molecules in the atmosphere are react with the infrared radiation. So that they gain the heat from that infrared radiation and again re-emit. So the CO2 and all greenhouse gases, okay, CO2 and all greenhouse gases are like you can say when the when the infrared radiation are there, then they will gain the heat from those radiation and again they will emit. So in this way, the atmosphere, like suppose CO2 molecule is there, that will receive the heat from the Earth's atmosphere, from the Earth's surface, and that will heat and again emit the heat in all direction. So this heat, this reflection will increase the amount of heat in the atmosphere. So in this way, the whole atmosphere temperature will increase. So basically, the average temperature of the Earth will increase. So this is the greenhouse effect. Okay. So the greenhouse gases will react in the infrared radiation. They will trap the heat. They will again reflect in more direction, and in this way, the heat will not leave the atmosphere. The maximum heat will only remain in the atmosphere, and the average temperature of atmosphere will increase. Okay. Because some of the infrared radiation passes through the atmosphere, some is absorbed and re-emitted in all directions by greenhouse gas. This is a very important statement, that it is absorbed and re-emitted in all directions by the greenhouse gas molecules. The effect of this is to warm the Earth's surface and lower atmosphere. So it will increase the Earth surface and lower atmosphere temperature. Infrared radiation is emitted by the Earth's surface. So when the shorter wavelength radiation will strike the Earth, then the reflected radiation will be in infrared zone. Okay. So this infrared radiation is coming from the Earth's surface, and that will trapped by the greenhouse gases. So this is the way in which greenhouse gases are affecting the Earth's atmosphere, and this is the way how the global warming is happening. So basically, suppose this is the molecule of a CO2 greenhouse gas or CH4, you can say. So it will take the infrared radiation and again it will absorb the radiation and emit it in all direction. So suppose this is the Earth. So it will emit in the every direction. So more heat, the heat was reflected, but again this molecule is reflecting the heat towards the Earth again. So in this way, this will move on. Okay, so every molecule will again emit, and in this way they will increase the temperature of the Earth's surface and surrounding atmosphere. So these are some important greenhouse gas, very and how they are produced and what is the lifespan and what is the natural effect on on the on the global warming and the human made effect on global warming. So first is the carbon dioxide, CO2. So it is produced from the deforestation, animal respiration, burning biomass and burning fossil fuels. So these there are some other reason also. These are the major reason: deforestation, animal respiration, burning biomass, burning fossil fuel. So once suppose a molecule is in the atmosphere, so lifespan of that molecule is 100 years. So suppose you are emitting one molecule today, so that molecule of CO2 will remain in the atmosphere for 100 years. So this lifespan is very high, 100 year. Okay. So how much CO2 we are emitting? That CO2 will eliminate after 100 years. So see the impact. Okay. If you emit more CO2, so that CO2 is accumulating in the environment and that will affect the atmosphere balance, and that is the main reason of global warming and climate change. Okay, because it will only eliminated after 100 years, so lifespan is very more. Now the natural effect on global warming around 25%, because suppose animal respiration is there, we are also breathing out CO2, so the natural effect on 25%, that is okay. But human made effect on global warming 70%. So that 25% was already there in atmosphere uh, before our industrial revolution. So that was not hampering the global warming, but the 70% you can see it's around thrice the this 25%. So that is the main reason. So human made effect on global warming is 70%. So we have to reduce the emission of CO2, carbon dioxide to the atmosphere. Then only we can mitigate the global warming and climate change. So second one is methane. Methane is also a greenhouse gas. It's produced by wetlands, agriculture, livestock. Okay, and flaring also, industrial flaring is also containing CH4. Okay, industrial industries, they flare some gases from the boiler and from from the other processes. Okay, so the flare is having some amount of CH4. So that is also a reason. So lifespan of CH4 is 12 years. So lifespan is 12 years is very less as compared to the CO2. Natural effect on green in global warming is little, so it's less than 1%. But human made effect on global warming is 24%. So you can see it's a high impact is from the human made only. Nitrous oxide, N2O, is fertilizer use and chemical industries. Again, the lifespan is 115 years, 115 years, very high lifespan. Effect on global warming, a little from natural effect and 6% from human made. Ozone, industry, natural process in upper atmosphere, lifespan is very short. Okay, 8% natural effect and O2 levels are dropping due to chlorofluorocarbons. So this is the main reason. If the ozone layer is protecting us from the UV radiation from the sun, okay, so our chlorofluorocarbons emissions are they are depleting. They are main reason of depleting the level of O2 levels in our atmosphere. So that is also a very big concern. Chlorofluorocarbons, CFCs, again man-made, used in air, used in consumer goods, 1,000 years. So chlorofluorocarbons are having the maximum lifespan, 1,000 years. If today we are emitting one molecule of CFC, then that molecule will only deactivate after 1,000 years. Natural effect, none, because nature is not emitting the chlorofluorocarbons. The all chlorofluorocarbon is human made only. Potentially high, but destroy ozone. So very high potential is due to the man-made, and it's destroying the ozone layer. If the ozone layer will not there, then the ultraviolet radiation will come to the earth in more percentage. And we have earlier seen that ultraviolet rays are having more energy, and that can hamper the DNA, and that can hamper the uh, living beings. So ultraviolet radiation is very dangerous. The last one is water, H2O. So its evaporation at the rate linked to the temperature, okay, constant circulation. So it's a natural process, cloud formation and all. It's in constant circulation. Natural effect on 60%, human made, it's unclear. Okay. So it's not an issue. The major issue are CO2, methane, nitrous oxide, ozone, and CFCs. Okay. So all over the world, every country is taking various measures to mitigate the global warming. And today we are working on carbon capture and utilization, CCUS. It's called carbon capture and utilization and storage. So basically every process which is emitting the carbon dioxide, so we are trying to capture that carbon, and we are trying to utilize that, and we are trying to store that carbon and to utilize in future applications. Now this is a basic diagram, okay, of the world map. So this is like you can say a month of March, and this just representing the temperature. Okay, the red one, this area is having high temperature as compared to this lighter sky blue area. Okay, you can say this B and C, and this one is A. So A is having more temperature as compared to B and C. So what is the effect of global warming? Okay, so this upper part is, you can say, why it is suppose frozen. Okay, completely frozen glacier is there. So this is the boundary. Okay, this is the boundary, you can see, when the atmosphere is balanced, atmosphere is natural. Okay, in natural condition, this concentration of CO2 is balanced, there is no effect of global warming, suppose. And suppose we are at current level, so this is the boundary. If we continue to use the fossil fuels, so CO2 level will increase, so the average temperature of earth will increase. Okay, then what will happen? So then this line will shift upwards, so this line may be come to this point. This is only symbolic representation, you can say, like suppose only this line shift only 1 centimeter, 2 centimeter upward. So in that centimeter, suppose this is the area, so this is area currently frozen, but due to the increase in temperature, okay, due to the increase in temperature, the iceberg will start melting, and iceberg will start melting, and the sea level will rise. Okay, the sea level will rise, and that increased sea level will affect the surrounding countries and surrounding areas, because the all seas are connected. So the sea level will rise, and that will affect all over the world. Okay, and we also know that iceberg is reflecting the heat. Okay, so if the iceberg reduced, okay, so it means that less heat will be reflected now, so it will increase the earth's temp, so the radiation absorbed by the earth will more, because the less will be reflected. Okay, so it will again increase the temperature of the earth. So in this way, if we do not control the current situation, then this will make a chain. Okay, this will make a chain, and that chain will increase the temperature in every way. Okay, because only suppose only this much of you can say it's very slightly, but the effect will be very huge, because the iceberg will be reduced. Okay, and the reflection of the sunlight will reduced, so overall temperature of earth will more increase. Suppose if 1 degree increase in average temperature of earth, then that 1 degree will affect all the earth atmosphere, and have that have potential to further increase temperature to more degrees. Okay, because the current situation of the current atmosphere, the balanced atmosphere, is the result of million of years. Okay, so millions of year has passed, and after that, we got the today's condition only. Okay, so if we again disturb the today's condition, we disturb the balanced atmosphere condition, then the repercussion will be more. If the 1 degree temperature increase, then it will make a chain of different phenomena, and those phenomena will further increase the global warming. Okay, so we have to stop it here only. We have to maintain the basic temperature of the earth. We have to reduce our energy consumption. We have to reduce the consumption of fossil fuels. We have to move toward the renewable or green energy. Then only we will able to maintain the current temperature of the earth, and we will break this chain of global warming, and that will only the best option for the survival of the living being or human being. Okay, so this is again like just representing the how this is happening, like the sun is same, the earth is same, but why the change of, you can say that this area A is having more temperature as compared to area B and C. So the reason is the shape of the earth, because the shape of the earth is not straight. Okay, it's in a spherical form. So this particular area, you can say this only area is receiving this amount of heat, but when we go the upwards, this area will increase. So heat is more distributed. So this particular area will have more temperature as compared to this area. Okay, because the amount will be same, but the area has increased. So the temperature will be less as compared to this. Okay, now come to the next. Okay, so there's a simple question. Like 40,000 years ago, atmospheric CO2 concentration was space, and this is determined using bubbles of space trapped in ice. Okay, so anyone want to answer? We have discussed this in our, I think, starting slides in slide number 2 or 3. I think we have discussed it. So anyone remember? The question is 40,000 years ago, atmospheric CO2 concentration was, and this is determined using bubbles of trapped in ice. So I have told you that there are some scientific methods, because when the ice formation in is there, then some bubbles are trapped in between the ice. So so which bubbles? Okay, it's air or CO2. Only two options are there: air or CO2. Anyone? Anyone want to answer? Okay. So these are air bubbles. So in when the ice is formed, so some air bubbles remain trapped in the ice. So we can do some like carbon dating or various different techniques are there. So from that we can find out the exact time span for that particular molecule. Okay, and we can also measure various like what was the concentration, and like if the air molecule is trapped, then we can find out the composition of air for that particular, and we can find out the time period of that particular molecule. In this way we can find out the CO2 concentration. So 40,000 years ago, atmospheric CO2 was not more than 300 ppm. So not more than 300 ppm, and today it's more than 400. Okay, so the correct answer is not more than 300 and air. So this option is correct. Again, question number 4, we are having a statement like glaciers are melting due to increasing CO2 percentage in the atmosphere, and we are having some two conclusion, like CO2 traps the energy which comes from sun. More CO2 in atmosphere means more absorption of energy released by earth. So just try in 1 minute and tell me the answer. I'm having some water. So the question is, glaciers are melting due to increasing CO2 percentage in atmosphere. So as we discussed in our previous slides that if CO2 is increased, it means CO2 is a greenhouse gas. So CO2 will trap the heat and reflect back the heat in every direction. Okay, because it's a greenhouse gas. So yeah, it's a reason glaciers are melting due to increasing CO2 percentage, because CO2 percentage means greenhouse GHG gases are increasing, and that are the reason of global warming. So that is the reason of glaciers melting. So what are the conclusions? CO2 traps the energy which comes from sun, and more CO2 in atmosphere means more absorption of energy released by earth. So yes, both are right, because if the CO2 traps the energy, because suppose energy is going towards the space from earth's surface. So the energies were going, okay, now the CO2 molecules are there in between. So they will again reflect back this energy. Okay, they will trap and reflect back. So this energy will again coming to earth, again going, again trapped. So again coming, again going, again coming, again going. In this way, the CO2 traps the energy which comes from the sun, and more CO2 in atmosphere means more absorption of energy re-released by the earth. So both conclusions are correct from the given statement. So conclusion A is right, conclusion B is right. So these are the correct options. Now world's total energy uses is the same as energy received by the earth from sun in. So world's total energy use, how much energy is used? 500 exajoules. And sun is releasing around 5 million exajoules. So the world's total energy use is the same as the energy received by the earth from sun in, we have discussed, in around 1 hour. Okay, so in 1 hour we receive the total energy that is sufficient, that is the annual consumption of the whole world. Okay, so from sun in 1 hour we receive the whole consumption of the energy for the world in 1 hour only. So now we are also having option in days, so convert this 1 hour into days. So in 1 day we are having 24 hours, so divide this way 24, it will come around 0.041 and something. So around 0.042 days is also correct, and 1 hour is also correct. So the correct answers are 0.042 days and 1 hour. Okay. Now next. So what are the various options possible to maximize energy received by a planet from its star? So what are the various options possible to maximize the energy received by planet from its star? So I think the professor have already covered uh, this in his lectures. That is the increasing surface area exposure of the planet, bringing the planet closer to the star, and using Dyson sphere method. So these are three techniques by which we can maximize the energy received by the planet, because suppose this is the star, okay, and Earth is rotating in this particular orbit. Okay, so the radiation is coming in this complete orbit. Okay, but the Earth, the area which is receiving is very less. Okay, so if we bring this planet closer to the this side, then the radiation, suppose the energy will content at this will be more, it will receive more area, it will receive more energy, okay, because the area will be less, because the radius will be, suppose if it is here, then this is only, this area is there, so the radius is decreased, so the per unit energy will increase. So now the earth will receive more energy, so we can do bringing the planet closer to the star, this will increase the energy, yeah, correct. Now increase surface area exposure to the planet, so we can suppose this area is only, suppose we have considered only a circular part, okay, because earth is in spherical form, but only the one side is receiving the area at a particular time, so we have considered a circular part or circular ring of that particular sphere, so only that part is receiving the energy, so we can increase the surface area exposure of the planet. If we, by any method we are able to increase the surface area, it means that more energy, more surface is, suppose this is increased by this, okay, so means more surface area is there to receive the energy, so automatically the energy received by the planet will increase. Or Dyson sphere method. Dyson sphere method is also there, like we can do some imaginary sphere. We can put a blanket all over the earth to receive the maximum energy. So you can also refer the professor's notes for this Dyson sphere method. Now the temperature of the sun surface is approximately. So I think in first slide we have seen this. What is the temperature of the sun surface? So there are multiple options like uh, 10,000 Kelvin, 5,500 degrees centigrade, or constant or similar in order to magnitude of the temperature attained during arc welding. So this is correct because it's around 5513 degrees centigrade, I think. So it's around correct. 500 degrees centigrade is correct, and it's when we are doing the arc welding, the temperature at the particular points are also similar to this. So the correct options are 500 degrees centigrade, similar in order of magnitude to temperature attained during arc welding, and constant. It's also constant because the earth, the core of the sun is having millions degrees centigrade temperature. So if the suppose earth is radiating some heat, but this core is again conducting heat to the star, to the its surface. So the surface of the sun will remain at constant temperature, and that will radiate the heat at that particular same temperature. So both three options are correct. The temperature of the sun's surface is approximately constant. It is around 5,500 degrees centigrade, and it is similar in order of magnitude to the temperature attained during arc welding. So these both three options are correct. Now arrange the following in their increasing order. So we have given first is radius of Earth orbit, then Earth radius, then Sun radius. So even starting slide we have discussed that at the center point, suppose this is the Sun. So here is Earth. Okay. So this is the orbit in which Earth is rotating. Okay. So the radius of this orbit was around millions kilometer. The radius of Earth is around 6,000 kilometers, and the radius of the Sun is around 0.7 million kilometer. Okay, so you can see from this data that Earth is having lowest radius. After that, the radius 0.7 kilometer Sun, and after the radius of the this orbit. So we have to arrange in increasing order. So first will Earth radius. Option A or option B can be. Option A can be correct or B, because both are having Earth radius at first. After that, Sun radius. So yeah, Sun radius, and after that radius of the Earth's orbit. Option A is correct. Because radius of Earth's orbit is highest. After that, the Sun radius, and after the Earth radius. So correct option is option A. Now question number 9. At any given point of time, one side of Earth radiates energy obtained from the Sun back to the space. So at any given point of time, one side of Earth radiates energy. Suppose this is the Earth in spherical form, and this is the Sun. So suppose this part, okay, this A part, this B part. So this A part is facing towards the Sun. So the solar energy is coming towards the A part only. Okay, but the B part is not towards the Sun. So this A part is having daytime. So that if A part is having daytime, then B part will have night time. Okay. So A part is having daytime and this B part is having night time. The question is, at any given point of time, one side of Earth radiates energy obtained from the Sun back to the space because it is night on the Earth side of the Earth. Yeah. So because this part is receiving the energy because radiation is coming, but uh, this is a particular time. But we know the Earth is also rotating. Okay. So the part which is not receiving sunlight now, maybe before 12 hours, it was in daytime. So at that time, the surface of the Earth has already absorbed some amount of heat. Okay, we have discussed the data that how much heat is Earth is absorbing. So that absorbed heat will be again reflected back, because now that this is open space. So this area of space is also receiving the heat, and this is also in, because the space immediate after the Earth. Okay, so it's again in the reflection in the shadow of the Earth. So this immediate space will also not receive the energy from the Sun. So the temperature difference will be there. So the temperature of the surface of the B as compared to the temperature of the space, okay, towards it will be less. So the Earth will radiate heat to the space. Okay. So what are the correct option can be? So the correct options are, it's night side on the Earth. Yeah, correct. And temperature of the side of the Earth is more than that of the dark side of space. So, so the correct options are, it is night on the side of Earth, because that side is radiating energy. So it means that that side is having night time, and temperature of that side of the Earth is more than that of the dark side of the space, because that dark side of the space is also in the shadow of the Earth. Okay, so that space is also not receiving the radiation of Sun, and we know that the space is not having any matter, so the space is not able to retain any solar energy. Okay, so it means that area is having very low temperature. So there will be temperature difference. Okay, because Earth have already retained some solar energy, so that will radiate to the space. Question number 10. So the intensity of sunlight incident on the Earth is higher during the space than space of the day. and therefore a solar device capture space light during that part of day. So in one slide we have discussed that suppose this is the earth, okay, and this is the sun. So earth is also rotating and also moving. So in our daily life we can see that at morning time the intensity of sun, the intensity of the solar radiation is low as compared to the noon time and as compared to the evening time. Okay, so we can directly conclude that intensity of sunlight incident on earth is higher during the middle, or you can say noon time, noon or middle. Okay, then morning and evening, because the morning and in evening the location of the particular area, it's so because the earth is rotating, so that location is receiving less energy, because we have seen that suppose at morning time you are at this area, so you will receive more heat, but after suppose the earth is, so after evening time you are at this area suppose, so you will receive less heat, and night time you will come to this area, so it will be dark. Okay, so the correct options are middle. Okay, so the intensity of sunlight incident on the earth is higher during the middle than morning and also then evening of the day, and therefore a solar device captures more light during the part of the day. That is also, we know that the maximum solar radiation is received in the middle time. But today we are also having uh, equipments in which, oh, this is your PV cell, so they will work on the sun tracking. So they will track the sun. They will move as the sun moves. Okay, as the earth rotate. Okay, so they are moving so that the angle of incidence of sunlight is perpendicular. So now we are having some basic questions, quiz questions. I think you can participate. So the first is, the size of the planet decides how much energy from the sun reaches the planet given a fixed orbit. The size of the planet decides how much energy from the sun reaches the planet given a fixed orbit. True or false? Anyone? Actually, this is an interactive session. If you will try to answer and we can discuss something about that. So it will be very beneficial for both of us if you participate. Anyone? Anyone online? I am again repeating the question. The size of the planet decide how much energy from the sun reaches the planet given a fixed orbit. This statement is true or false? I am also giving you hint, as we have already discussed that suppose this is the earth and this is the sun. So we are taking the particular area a circular disk. So if we increase that disk, suppose can be increased by any means in this area. So if the area is increased, intensity of the incidence radiation watt per meter square. Okay, so this meter square is area. If your area is more, it means you will receive more wattage. Okay, it means you will receive more energy. Okay, so suppose uh, the area is 1 meter. Sure. Suppose, so you will receive only 1 watt. If area is 2 meter square, you will receive 2 watt of energy. So you can see if area is twice, the energy is also become twice. So if the more area means more energy will be received. So that is the question. The size of the planet. If size of planet increase, it means that the area which is receiving the solar radiation or which is exposed to the solar radiation is more. So that means that area will receive more energy from the sun. So this statement is true. So the size of the planet decides how much energy from the sun reaches to the planet given a fixed orbit is true. Now second one, there is a close link between GDP of a state and the power consumed by the state. So there is a close link between GDP increased by the state and power consumed by the state. So I think in our first slide or second slide we have discussed about this. So anyone want to answer this question? This statement is true or false? There is a close link between GDP of a state and the power consumed by the state. So this question is saying that if the GDP is increasing, means the consumption of power for that state is also increasing. So I think it's true because if your GDP is increasing, it's mean that you are producing more, you are exporting more. Okay. So when you are producing more, it means you are using the more energy. Okay. So basically, the GDP is linked with the power consumption. The more power consumption means more resources are available, more energy is used by the processes. So the GDP is directly linked with the power consumed. So it's true statement. Now come to the third one. A hypothetical Dyson sphere will capture all of the energy from the sun coming to the orbit of the Earth. So in a hypothetical Dyson sphere, so the Dyson was a scientist, or he was saying that we can make imaginary sphere around the Earth, or you can say blanket around the Earth. So that will capture all the radiation coming towards the Earth's orbit. It was imaginary but very nice thought. So yeah, it's true. Fourth one is there is strong need to change the source of energy used by the world. A very important question. There is strong need to change the source of energy used by the world. True or false? And what is the reason? Anyone want to express their thoughts on this? Anyone? Is it correct? Is it true or false? The question is there is strong need to change the source of energy used by the world. As we have already discussed that in our previous classes also, we have discussed about the concentration of CO2 in the environment. Okay, so the current concentration will be double in around 88 years. So the current ppm of CO2 will be doubled in the current amount of CO2 in the atmosphere will be double in 88 years. Okay, so if the amount of CO2 is increasing, it means that greenhouse gases in the atmosphere are increasing, and we know that if the greenhouse gases are increasing, so they will trap more and more heat because every greenhouse molecule is trap the infrared is sensitive to infrared radiation. So the earth at the earth surface emit the radiation in infrared wavelength. So the greenhouse gas molecules will trap the heat and again re-radiate that heat in all direction, and in this way that molecule will increase the average temperature of the earth, or that molecule will show the effect of increasing temperature on the earth. So yeah, there is strong need to change the source of energy used by the world, because if we do not change the source, if we continue to follow the fossil fuels, then we are increasing the GHG emissions, and GHG emissions are connected with the global warming and climate change. So GHG emissions are directly connected to the global warming and climate change, and when the global warming is there, the result of global warming is that we will see the extreme condition of every climate. If suppose there is a winter condition, then we will see the extreme winter. If summer, we will see the extreme summers. Okay, so the global warming will rise the temperature, average temperature, and will results in extreme conditions. Okay, with will extreme weathers. So that is very dangerous for our environment. So there is strong need to change the source of energy used by the world. So its statement is true. So what is the best possible way to change the source of energy? Anyone want to discuss? What is the best possible way to change the source of energy? What are different possible ways? And today class also we have discussed that the world energy, annual energy consumption by the world, sun is giving only in 1 hour. So we are receiving the total annual consumption of energy in just 1 hour. Okay. So if we are able to develop some technology that can tap off the maximum amount of that energy, so either we can complete our having huge scope there. Okay, because in 1 hour you are receiving the annual energy consumption. So suppose you are having technology with only suppose 20% efficiency, okay, in 15% or 15% efficiency, you will capture the energy in maybe 3 days, 4 days, 5 days for the annual consumption. So we are having huge scope for it. We are also moving toward the hydrogen economy. We are also moving toward other renewables. We are also moving toward wind energy. So there are various ways all over the world we are focusing. So basically, we are moving towards the clean energy. So only the clean energy or renewable energy is the option to handle the current situation and to handle the global warming and climate change issues. Now come to the last question. Question number 5. The solar spectrum that reaches the surface of the earth is impacted by the gases in the atmosphere due to wavelength that they absorb. True or false? Anyone? Anyone? The solar spectrum that reaches the surface of the earth is impacted by the gases in the atmosphere due to the wavelength that they absorb. As I have already discussed in the class that greenhouse gases greenhouse gases are sensitive to the infrared wavelength. Okay, they are sensitive to the infrared wavelength, and the energy emitted by the energy reflected by the earth's surface is in the infrared wavelength zone. Okay, so mm, they that's why those molecules trap the energy and reflect back that energy. Okay. So if the reflected energy in UV wavelength, then the greenhouse gas will not that will not you can say impacted by the UV radiations, but the infrared wavelength is reacted with the GHG gases. Okay, so yeah, this statement is true. The solar spectrum that reaches the surface of the Earth is impacted by the gases in atmosphere due to the wavelength that they absorb. Okay, because the GHG gases absorb the infrared wavelength, they will not absorb the UV wavelength or other wavelengths. Okay, so they are sensitive to the wavelengths. So it depends on the gases. Okay, because the Earth's surface will emit the infrared. Okay, so we need to. So the greenhouse gases are defined. Those will absorb the the infrared wavelength. So this statement is correct. Yeah. So you can see that all statements are true. So again, just revising in short form. So the first question was the size of the planet decide how much energy from the sun reaches the planet gives a fixed orbit. So it was true. Second one was there is a close link between GDP of a state and the power consumed by the state. As we discussed, it's true. A hypothetical Dyson sphere will capture all of the energy from the sun coming to the orbit of Earth. Yeah, true. There is a strong need to change the source of energy used by the world. Yeah, it's true. The solar spectrum that reaches the surface of the Earth is impacted by the gases in the atmosphere due to the wavelength that they absorb. Yeah, it's also true. So these five questions are all true. Now the conclusion. So from our discussion and from based on the lecture given by the professor, we can these are the conclusion actually. So the first one is solar energy is absorbed and released through a wide range of phenomena on Earth. So the first one is solar energy is absorbed and released through a wide range of phenomena on Earth. Yeah, it's correct. As we have seen in our slides, that clouds are absorbing the solar energy, atmosphere is also absorbing and releasing, and the earth, like water is absorbing, the earth surface is absorbing and reflecting. So there are various phenomena, wide range of phenomena on earth are there that are absorbing and releasing the solar energy and dependent on the solar energy. Second one is geographical location and seasons are important aspects impacting solar energy received by a specific location. Yeah, this have also we have discussed that location is very important because some locations are in direct, you can say the perpendicular to the sunlight receiving, and some are at different angles. Okay, we have I think discussed this. Like this is the Earth, so the area at this location will receive sun more heat as compared to the area here. Because suppose if you are considering the equivalent light, so the area for that is more as compared to this location. So the geographical location and seasons are important aspect impacting solar energy received by specific locations. Now the time of the day is important parameter impacting the intensity of solar energy received. The time is also very important as we have discussed previously that at the noon time or you can say middle time we receive the maximum solar energy as compared to the morning time or evening time. Okay, that is also due to the geographical location. Okay, also time. Okay, so these are the conclusion. So now we are also having around 25 minutes left, so we can discuss something more. Yeah, we can discuss about this. Anyone want to? Anyone having any doubt? I think we have solved around 15 questions. So I think these questions will help you in your assignments. So you can submit your assignments before due dates. And for week 3 classes, I think this session will be very helpful to you, and you will be able to solve your assignments. If you are having any doubt regarding this class, please tell me. So just we can like summarize today's class from. So in this first slide, we have just like seen GDP and energy use, and we have seen that if GDP is increasing, it means that energy use is also increasing. In second slide, we have seen. In second slide, we have seen that five GDPs in India is also connected with the maximum power installed or allocated. Like Maharashtra, Uttar Pradesh, Tamil Nadu, Karnataka, Gujarat are having maximum power allotted or installed as compared to the states. Some states with lower power installed, like Arunachal Pradesh, Manipur, Nagaland, Mizoram. The GDP of these states are not as such as these 5 states. So this graph is indicating the correct results. Like if the power installed, if the power consumption is more, then GDP for that state is more. So in this slides, we have discussed one question like as the GDP of a nation increases, energy consumption again increases. In this slide, we were having again a question like Maharashtra consumes more energy than Tamil Nadu. So options, the correct option was like Maharashtra has more GSDP than Tamil Nadu. Yeah, correct. Because if more energy it's mean then GDP is more. Based on the trends usually seen in relationship between energy uses and economic activity in India. So B not follows. Tamil Nadu has more industrial output. Then if GDP of Maharashtra is more, then it means then output is also more for Maharashtra. So in this slide, we have seen that the average atmospheric concentration, CO2 concentration ppm, is increasing from last 60 years. You can say 1950, around 1960s to 2020. You can see that the CO2 concentration is increasing. And for last 20-30 years, you can see the slope of the increasing CO2 concentration is very high as compared to the past year. Okay, and the main point which is for which need to be focused here is that that CO2 in the air has never been above 300 ppm in last 4 lakh years. Okay, so it's very important. Like the current concentration of CO2 is around 425 ppm. Okay, so it's very huge, and if we are not control the current use of our energy, and if we will not control the fossil fuel consumption, this CO2 will double in coming 88 years, around 88 years, and this will be the major reason for average temperature increase of the earth. And this will like melt the glaciers, and again if the cycle of temperature increase is started, then that will move on. Okay, so that will again increase the more temperature. In this way, the human being and the living being on earth, life of those living beings will be very difficult. Okay, because current atmospheric condition are the result of millions of years, and if we are disturbing these condition, then the severity of the atmosphere will be there. So we need to face the consequences. So that's why all over the world we are shifting towards the renewable energy. That is very important. These are the some basics about the solar radiation. In this slide, we have like seen that solar radiation is the radiant energy from the sun, and it's provide light, heat for the earth, and energy for photosynthesis. And it's very essential for metabolism of environment and inhabitants. And there are three gaps, three bands or ranges. You can see the one is ultraviolet, visible, and the infrared. And the major infrared radiation tax makes up around 49.4%, while the visible light only provides 42.3%, ultraviolet only 8%. Okay, the amount of intensity of radiation that a location or body of water received depends on a variety of factors. So the factors are latitude, seasons, time of the day, cloud cover, and altitude. So these are very important factors: latitude, season, time of day, cloud and cover, and altitude. Now, not all the radiation emitted from the sun reaches Earth's surface. Much of it is absorbed, reflected, and scattered. So we have discussed in detail that how the clouds are absorbing, how the clouds are reflecting, how the atmosphere is absorbing, how the atmosphere is reflecting, how the surface of the earth is absorbing and reflecting. Okay, how the scattering is and how the scattering is done. Okay, so we have covered it in detail. And at the surface, so solar energy can be absorbed directly from the sun, called direct radiation, or from light that has been scattered as it enters the atmosphere, called indirect radiation. So these are the diagrams in which we can see the peaks between the peaks of a wave. The distance between the peaks of a wave is denoted the wavelength, and it measured in nanometer. Okay, so the sunlight is in three band gaps: UV, visible, and infrared. And it's and the wavelength vary from 100 nanometer to 1 millimeter. So the sunlight or solar radiation spectrum includes bands between 100 nanometer to the 1 millimeter, which encompasses the ultraviolet, visible, and infrared radiation. So in this diagram, you can see that there are three colors: blue, green, and red. Okay, and the wavelength cycles are measured in nanometers from peak to peak. You can say this peak to this peak, measure the wavelength. Okay, the shorter the wavelength, the more energy it has. So if the this wavelength distance is short, mean the wavelength is less, then that will having more energy. Okay, as compared to the longer wavelength. So in this diagram, you can see there are three wavelengths: blue, green, and red. So we can see that the distance between the peaks for the blue, see that like from blue here to here. Okay, so see the distance. And for green, so A is for blue, B is for green, and C is for red. So we can see that C is greater than, we can see that C, the distance, the wavelength for C is greater than, for B is greater than for A. So A is the shorter wavelength, B is in middle, and C is the maximum wavelength. Okay, so the energy with A will be highest as compared to B and as compared to C. So in sunlight, there are three band gaps for UV, visible, and infrared. So UV comes under A, visible comes under B, and infrared comes under C category. Okay. So these are the color representation for. So the blue color is representing the UV light, UV radiations, and the green color is representing the visible radiation, and the your red color is representing the infrared radiation. I think you have heard about RGB, red, green and blue. Okay, so these are RGBs. These are the colors. From these colors, different color of can be made. Okay, so in this diagram you can see this is the blue color. Okay, this is the red color. In between there is green color. Okay, and this invisible spectrum you can see the multiple colors. Okay, but major are red, green and blue. Okay, so this UV light is having very around 8% of contribution in the heat. This infrared is having around 49% contribution, and this visible spectrum is having 42% of contribution. Okay, and the UV light wavelength range from 100 nanometer UV from 100 nanometer to 400 nanometer. The visible light is from 400 to 700 nanometer, and for infrared it is 700 to 1 mm. So these are the range. Okay, from this diagram you can see. And in this slide it's also very important. We have seen that how much of energy is Earth receiving from the sun. Okay, so sun gives out around, we have already seen that 384 iota watts. Okay, so sun is giving out 384 iota watts, and 384 iota watts means 310 to 24 is iota. So this is the radius of the orbit. This is the radius of the sun. 0.7 million 6371 kilometer radius of Earth. Okay, so this is the sun. It's emitting radiation in this particular orbit. Okay, so we can find out the intensity first. What is the intensity of sun's radiation at Earth's orbit by using the total radiation that is given by the sun and by dividing the area of that particular orbit. So we know the orbit is in spherical form. So 4 pi r square is the area. So you can put the radius of that orbit and you can find out the intensity of sun radiation in this Earth's orbit. So that is 1377 watt per meter square. So this is the intensity of sun's radiation at Earth's orbit. Now we have to find out that how much of this intensity, how much of the energy is receiving on the Earth's surface. So we can find out the area of the Earth. We know the radius of the Earth, so we can find out the area of Earth. We can like decide the sun is. So this is the a disk. We can consider it a circular disk. So the area will be pi r square. So you can put the radius of the Earth here r. So pi 3.14 into r is 6.371 10 to the power 6 ka square. So you will get this data. So you are having the area, you are having the intensity. So multiply. So when you multiply, so you will get power received from the sun by the Earth. Okay. So basically you are having the intensity, you are having the area. So you can multiply. So you will get the power received from the sun by the Earth. Okay. So in this way, the energy received from the sun by Earth each year, this is in watt. So 1.75 into 10 to the power 17 watt or joule per second. So you can convert into the joule. So multiply 60 into 60, 60 for minute. 64 hours, 24 hours in one day, and 365 days in 1 year. So after multiplying, you get 5.5 into 10 to the power 24 joule. Okay, so you can write 5.5 into 10 to the power 6 into 10 to the power 18. Okay, I can write 24. 10 to the power 24 is 10 to the power 6 and 10 to the power 18. So I know that 10 to the power 18 is exa, like 10 to the power 24 is iota and 10 to the power 18 is exa, and this is million. So I can write 5.5 into 10 to the power 24 joule as 5.5 million exajoules per year. Okay, this is very important. You have to know about the units. So 10 to the power 18 is exa, 10 to the power 24 is iota. So I can write 5.5 into 10 to the power 24 joule as 5.5 into 10 to the power 6 into 10 to the power 18. So 10 to the power 18 considered as exajoules and 10 to the power 6 is million and 5.5 is there. So it is 5.5 million exajoules per year. So from our first class, we know that humankind uses 500 exajoules per year. Earth is receiving 5.5 million exajoules per year. Okay, so you can divide both the figures. So when you divide the 500 by 5.5 into 10 to the power 6, you will get around 0.033 days, or you can say 0.79 hours. And you can also consider like only 70% of incident radiation is utilizing in the energy. So because 30% is reflecting back, so divide this 0.79 by 70, you will get 1 hour. So this 1 hour is very less as compared to the 1 year, because suppose in 1 year we are using 500 exajoules and only in 1 hour we are receiving this much of energy from the sun. So we are having huge scope to tap off the energy, the clean energy from sun. Okay, so all over the scientists are working towards it. So the conclusion from these slides is Earth receives nearly 5.5 million exajoules of energy from the sun each year, and the entire energy used by the humankind each year is received on surface of the Earth from the sun each hour. So these are some important data. So anyone is having doubt regarding this? So I'm just changing the slide. If you are having any doubt on a particular slide, you can please let me know. So in this slide, we have discussed about the Earth's energy budget. In these slides, we have discussed about the greenhouse effect, like how the greenhouse gases are increasing the average temperature of the Earth atmosphere, how they are trapping the heat. Okay, so the major outcome from the slide was that infrared radiation, because the greenhouse gases, because the Earth is radiating infrared radiation only, and the greenhouse gas molecules are sensitive to infrared radiation. They absorb the infrared radiation and they emit that heat in every direction. So in that way, the greenhouse effect is happening. So in this slide, we have seen different types of greenhouse gases and how they are produced and what is the lifespan of those gases and what is the natural effect on global warming and the human-made effect on global warming. So the major gases are, you can say, the carbon dioxide, methane, nitrous oxide, ozone, chlorofluorocarbons, water, and the point to be focused here is that carbon dioxide is having 100 years of lifespan. Okay, and the human-made effect is 70%. So we have to reduce it because we are contributing 70%. Okay. The next is in this slide we can see the for a particular month like March, we can see the temperature of different zones on the Earth's surface. The central part is having slightly red, so it's mean receiving more energy as compared to the upper parts. So if the average temperature increase, so that will affect all over the world. In these slides, we can see how this middle area is temperature is more as compared to the top and bottom areas, because the intensity is same, but the area is increased when we go from upwards as compared to the downwards. Again, we have discussed some questions here. So yeah, we have already covered it, like CO2 concentration of 300 ppm and determined using air trapped in the ice. This again, we have question discussed. If you have any doubt, please let me know. These are the answers. This is again question like total energy used in same day, same as energy received by the Earth from Sun is. So we have seen the all calculations, like it's around 1 hour we have received total energy. Okay, and if you convert the 1 hour in days, so it will be around 0.042 days. So various options possible to maximize energy received by the planet from its star is these. Surface area, you can increase surface area, you can bring the planet closer to the star. You can use Dyson sphere methods. So you can temperature of the sun. So we have seen that it's constant. It is around 5500 degrees centigrade, and it is also similar in order of magnitude to the temperature attained during arc welding. So both these options are three options are correct. So arrange the following in their increasing order. So we have seen that the orbit of the Earth rotation is having the maximum radius in millions. Okay, and after that the radius of sun is around 0.7 million kilometer, and then the radius of the Earth, which is around 6200 something kilometer only. So if you want to arrange in the increasing order, so the correct answer will be Earth radius, then sun's radius, then radius of the Earth's orbit. Now at a given point of time, one side of Earth radiates energy obtained from the sun back to the space because it is night on that side of the Earth. Yeah, because if the night, then the temperature, because in daytime that surface of the Earth has already absorbed the radiation. Now the sun is not facing towards that area, so as compared to the space, there is a temperature difference, so Earth will radiate heat towards the space. The temperature of the side of the Earth is more than that of the dark side of the space. Yeah, correct. The intensity of sunlight incident on Earth is higher during the middle time, we know, okay, as compared to the morning or evening, and therefore solar device capture more light during the part of the day, because in daytime the sun is facing, so that will receive more light. So correct options are middle, morning and more, middle, evening and more. So these are some statements we have just seen. The correct answer are all true. The size of the planet decides, yeah, how much GDP. So it's correct, yeah. The link between GDP and state's power consumption, yeah, it's again correct. Hypothetical Dyson sphere will capture all energy, yeah, correct. There is strong need to change the source of energy, yeah, correct. Otherwise, the average temperature of Earth will increase, and the environment will be not habitat for the species. The solar spectrum that reaches the Earth of the surface is impacted by the gases in the atmosphere. Yeah, it's correct, because the greenhouse gases are sensitive to the infrared radiations. So thank you very much everyone for today's class. So in today's class, we have discussed about week 3. We have done some sample problems, and we have revised the basic concept of the class. So I think these concepts are helpful to you for your assignments for week 3. Okay. So in next class, we will discuss the week 4 content. So I request you all, please come to the next class on Monday, 6 to 8 p.m. In live session 4. We will discuss about the week 4. Today, thank you for joining. Okay. So again, thank you everyone. So with this, I am ending this class. Okay. Thank you very much.